Right, welcome to today's Sendo Reliability webinar on failure analysis, actually. And I do have a few opinions about this, and we'll get into that as we go. And the, the idea of this whole series that I've been doing for the last couple of years called The Fundamentals is to, um, as much of anything, dive into a lot of the assumptions we make and the backbone for a lot of these things. It's one thing to implement a process or a procedure. It's another if you really understand it. And so a lot of what I've been doing has been going with this kind of stuff. Let's see. And I got another idea in the chat. I was asking before we hit record if there's any ideas for next year, the next 2026 series of events I'll be doing, if any themes or ideas or so on. And so I've got a couple so far. And if you've got any ideas for next year, if you're listening to the recording, it's not too late. Let me know. The schedule is always very flexible. Yet I'm looking for like a theme or an idea that would be both useful for you all and interesting to put together and talk about. So you can, if you're online, just let me know in the chat window. If you're in the recording, there's usually or there's always a comment field near where you're doing this. If you're listening to it on a podcast, come on to the site, and there's plenty of ways for you to get in touch with us. So on to today's, ride through failure analysis. So we don't often do failure analysis, although you can when you're investigating a new material, for example, you're trying to characterize the range of motion of something, and you use many of the same techniques and ideas in characterization work to see what it does and doesn't do. We also do it on purpose when we do HALT, H-A-L-T, and we cause a failure or two, and then we dive in to learn more about why it failed and what we should or shouldn't do about it. Yet most of the time, we have a prototype or a breadboard, or we have a mock-up of some sort, or early stage prototype all the way to manufacturing stage builds of our products or systems, or we put in an assembly line and we're getting it coming up to speed, and or it's in the customer's hands or it's in use and something goes wrong. And at that point, we have many choices to make, and we'll explore a couple of those. But the idea is that we generally then want to do something. We want to find a solution. And there's a meme out there that's been around for decades and decades where if it's moving and it's not supposed to move, use duct tape. If it's not moving and it's supposed to, use WD-40. If only all of our problems were that easy. And although duct tape and baling wire has many attributes, it might not be the right solution for your particular problem or issue. And so there's usually some emphasis, some idea that, oh, maybe nobody's been identified, but in general, we want to find a solution or a way to mitigate or minimize or avoid or restore whatever it is that's not working anymore. And one of the things I find the most difficult part of dealing with failure analysis is getting to a meaningful, useful, and verified short-term solution, but then really taking advantage of all that work it took to find the answer, to find a solution, and expand on that to make it a long-term solution and prevent other similar problems and other similar projects or similar issues and breakdowns and so on. And we'll certainly dive more into that, but it's part of, I think, just institutionally and culturally, once we get a short-term solution and it's off our plate, it's really, really, really difficult for us and or our organization to circle back and say, one, did it really work? And two, how do we learn from this? How do we avoid systematically other similar type problems? And that we'll spend a little bit of time on. But before I get too far into this, what's the first thing you do when a failure is discovered? Let me pause here for a sip of tea. And what's the first thing that you do with your organization, with your processes, with your intuition? What's the first thing when a failure is identified or discovered? All right, a couple coming in. Yeah, is it really a failure? It, yes, Juan, not sure I'm pronouncing that right. Sorry about that. Trace the population for them. Okay. It confirmed the failure. Yep. Good one, Chris. Kenneth has characterized the failure. You know, what failed? Confirm the failure and define emergency response action. There you go, Jersey. Um, yeah, if it's a 55-gallon barrel of high concentration sulfuric acid, which probably shouldn't be in one of those barrels, and it starts to leak, it's probably safety first, is, you know, evacuate the building or contain the damage or whatever response is first. It's really the answer I'm looking like. Yeah, call a FEA guy. Um, which item failed? Define the failure. Good, good. You're all in and around the right area, yet I would argue in most of our organizations and intuitively, if it's a safety related issue at all, or even considered to be one, it's it's help people be safe, you know, whether that's an evacuation or an alert or you know, wall it off or tape it off or do whatever, shut down the machines, those emergency stops we have on lots of our machines. It's get it safe first. Now, if it's a failure that is safe, it failed cold or it doesn't cause any issues for people or the environment and so on, or our assets, then it's, well, what failed? What do we know and don't know? And we'll certainly get into this in much more detail. But the first thing to do is one, recognize that it is a failure. And oftentimes that leads to a whole lot of discussion about what is a failure. Now, if there's a small scratch on a painted panel or a coated panel, is that a failure? In some organizations, it's not. And in other organizations, it is. For example, if this is a coating on the inside of an electronics box and that coating provides a electromagnetic radiation suppression or containment, is that scratch enough to compromise the shielding? If not, and you don't worry about aesthetics on the inside of your system, which some organizations do, then you may not call it a failure. But very quickly, with that simple example, you can see where this becomes a gray line. And oftentimes, that's the first thing after safety is it really a failure? Now, I always think of all these wonderful scientific breakthroughs that have occurred over the centuries when there was an accident or a mistake or some odd observation occurred, and somebody goes, oh, why did it do that? What happened here? And just a bit of curiosity then leads to all these interesting things. So every time I run into a failure, I get a little bit excited because I may have just, you know, landed on something that'll get me a Nobel Prize. Now that's just me, and that keeps me motivated to explore and be curious about failures. More often, it's we do a triage. You know, is this failure worth doing anything about? And oftentimes that first decision sets the stage of what happens next. And if we just ignore it or say that's not a big deal, or that's a one-off, I'm not worried about it, uh, or I really don't have the time to go understand this. In my mind, we're missing an opportunity to do something, to explore it and so on. Yet we have plenty of pressures and plenty of things on our desk already that we need to get done, that adding one more failure investigation is probably not high on your list. So it's a trade-off right at the first instance when you notice something. And that's a problem. So by default, or by my own personal bias, is when you see a failure, it's worth a few minutes as a minimum to investigate it. And especially like I had somebody tell me once they had 10 prototypes and one of the prototypes wouldn't start, wouldn't fire up and come alive and do what it was supposed to do. And they dismissed it as, well, it's just a prototype. And I says, well, if you don't understand what caused that prototype not to work, you may be building in a 10% failure rate in your field, in the field. Now, hopefully you have lots of other gates you got to get through before you do that. Yet, if your next prototype round is to make 100 of them and 10 of them won't start, now you're getting pretty late in the game. So let's not ignore even simple early failures with simple explanations. They're worth investigating. I often say, and sorry I didn't say it so far today, is failures are gold. It's a wealth of information about what happened, what went wrong. So first thing, safety. In every industry everywhere, and some are more, have more dangerous materials than others. But first thing is safety. Second is, what is this failure? And how do I gather the information around it? But I'm getting ahead of myself a little bit. So I'm going to talk about the 8D process fairly quickly, and there's plenty of stuff online about more details of it. It's called 8 disciplines, and it's an 8-step framework for doing failure analysis or problem solving, as some organizations call it. And I have found this process over and over and over again as being just so much common sense and so practical that I highly advocate for it. And there's many, you don't have to pay anybody to use this process. It's sort of like using 5 whys, which is one of the tools they advocate for. But the idea is that if your organization has this is the way we deal with failure analysis, then I highly recommend using as much as possible from the 8D process to do it. There's some pushback, there's some cons to it. Yet I think in the long run, it just makes so much more sense and gets to a solution that really is useful and practical, so much easier than about anything else I've ever seen. So that's why I really go to it. Now, the top issue here is that many people will say, well, you got to form a team. Well, I don't have time to work on this, and I'm not going to round up 3, 4 other people to go work on this thing. And that's the second decision. Once you identify a failure, is this something that really needs to be solved? And that may or may involve going into a fracas system and doing some triage, or if it's obviously a problem that needs solutions, then you dive into, let's form a team and describe the problem. There's a handful of other steps I would do early on too. One is treat the instance of the failure, wherever it is that you find it, as a crime scene. Don't destroy the evidence. Gather as much information as possible. And it's how was it noticed? Did it make noise? Did it jam? Did it do this? Did it do that? Did it not power? Did it create smoke? Did it whatever? What are the observables? How did you observe it? What was going on at the time? Who were the witnesses? What do we know? What's the process stages that we're in? What kind of, if it was shipped or not shipped, is this part of a batch or not part of a batch? On and on and on. Gather as much information as possible immediately, because that's when it's the freshest. And that's my advocates that would be a little bit different than what 8D does. Here I talk about how great this deal is, but is it safe? Gather the information and preserve the information as much as you possibly can so you can get to good failure analysis. But not every problem needs this. If it's, oh, wait a second, I'm not getting 5 volts here and I should, and I'm an electrical engineer and it's my circuit that I'm designing. All right, I need to change this resistor to some other value. Well, I can go do that, and I don't need a team to help me redesign my own product. And it might be part of the design process to start with, and so on and so on. So not every issue or problem is is goes to this level, and every organization sets this at a different tier, a different level of what constitutes a problem that needs a team. Now, often go the initial response, safety and gather the information, is often used in a failure reporting and corrective action system. And many organizations have those in one form or another. Some are more cumbersome than others. Yet the idea is that at that point, usually then it's a decision saying, no, this is more complex. We need people from different parts of the organization to really understand and solve this. And it may be because it's identified as a serious problem that could affect X amount of our production, or it's a quality issue that we need to reduce the variability of our product line because this is not staying consistent and we're not sure what's causing the consistency. If there's not part of somebody's already existing design or manufacturing engineering jobs and it goes into fracas, then it usually gets adjudicated as to, no, this is serious. We need to go solve this. Other times it's more informal and you say, we got to solve this, but I can't do it myself. So I'm going to go get Jill and Sarah and Mohammed, and we're going to form a quick team and go solve this thing. So every organization does this slightly different. Yet the idea of forming a team is that each of us bring different perspective. The design team brings design insights. The manufacturing team brings the process and the other thing, the details of how it's assembled or manufactured, and maybe even bring in somebody from the procurement area that knows the key vendors involved with whatever it is you're working on. But 3 or 4 people is all you need, but each brings a different set of skills. While it's possible to brainstorm all by yourself, it's a whole lot easier to do so with a team. And you get much richer and better results. Plus, you get to share the workload of how do you solve this thing. So, highly recommend getting the team together when it's deemed, yes, this is a problem or a failure that needs a good, solid solution. And it's one that's beyond anybody's day-to-day work that we want to do. All right. So the team's first task is describe the problem. And this builds on that initial identification of the failure is, well, what was going on? What do we know and don't know? What were the sounds, smells, so on of what was happening? And we use, things like fishbone diagrams and 5 whys and a handful of other tools that allow us then to get into fully understanding the problem. And as you already all know, is that somebody's going to walk into that and go, oh, I know the solution to this, and then walk back out and go try to do it. Now, sometimes people are just brilliant that way and have a gut sense that says, yeah, I know what that problem is. And they're right. Other times, it's a colossal waste of time. And you don't know that until you describe the problem well enough. And even then, you may not have details enough to actually solve the problem. So let's go into this a little bit deeper. If it's not safety and you preserve what I call the crime scene, then it's a matter of, well, what do we know and don't know? And how, if this was during production and it was involving, say, an op amp, how many other systems have that op amp? Or can we quarantine this? If this is a serious problem, let's pull stuff out of inventory and quarantine them, or off of trucks and quarantine them, or stop delivery for things that are on the boat, and so on. If it's a very, very serious problem, it's pull it off the shelves, especially if it's safety related. But the idea of the initial response is if this problem, especially safety stuff, is how widespread could it be? We may not have the evidence yet to know how widespread it is. And yet the idea of avoiding injuries to customers is a whole lot more beneficial than saying, oh, we'll just deal with that later, at least in the US. Worldwide, you might have a different approach to this. But the idea is let's contain the problem. If we find one failure and it's likely to affect, say, 50% of our production, well, let's not keep making 50% scrap is really the idea here. But the beyond defining the problem, it also very quickly goes into how do we mitigate or minimize the exposure of this identified issue or problem out to our customers or our production line. And so this one's usually pretty obvious. We often do this just to understand the scope of the problem. If I only have one prototype and we noticed a failure in it, the containment is really just that prototype, right? Yet if we're in production and we're making 1 million a day and we're seeing something that's systemic or possibly systemic in all of those units, well, it probably makes a whole lot more sense to shut the line down than it is to make a whole pile of stuff that we either need to repair or throw away. So it's a way to minimize the costs of that problem getting out of control or that failure getting out of control. Now, sometimes the failures come to us through a customer call or a warranty return or hopefully not through a investigative journalist, showing up at your site saying, why have you created this product that hurts people? But the idea is that once we identify it, it's really triage it quickly, understand in detail what is the problem, mitigate, contain where the exposure of this problem to causing failures is, and then we can get started into root cause analysis. And I'll come back to escape point in a second. But the idea is that we want to fully understand the problem. Can we turn it on and off is one way to do it. If I add 8 volts to this circuit, it fails. If I keep it at 5 volts, it works, right? Well, that's a way to turn it on and off, but hopefully that comes with a good understanding of that circuit as to why 8 volts causes a failure and 5 volts doesn't. Or it's materials, or it's if we load it this way with a counter turn or a counterclockwise turn versus a clockwise turn, it shears. All right. Well, why is that? Is there a mechanical stress concentration that one direction causes more force on the joint than the other? And so on and so on. And sometimes these things are pretty straightforward, but other times we have a clue, say a sheared bolt. And depending on how that bolt actually broke and what kind of forces were involved with it and the material composition of that bolt and so on, it may take us quite a while to sort out what are all the variables and ways to get to the actual root cause of this. Now, Chris Jackson talks in one of his webinars last year, I think it was, he has used a flak jacket, a bulletproof jacket in the colloquial that was made out of a fiber that when exposed to moisture or humidity changed its material properties so that it was much less strong than when it was first made or dry, and allowing bullets to penetrate it, which is not the purpose of a bulletproof vest. But the root cause of it got into the chemistry of the fiber's materials. And sometimes you really do need to get to that level to really understand what the problem is. Solving symptoms, as all of you know, I'm quite sure, is like a whack-a-mole. is some things can have many, many different symptoms, and we'll be trying to solve those all day long. Whereas if we understand the physics and chemistry of what's actually happening, and or the software interaction with the electronics, or the way a user uses it versus the way it was designed to be used, or how people make decisions as they're interacting with your product, any of those could lead you to an understanding of what the root cause is. And one way to do it is like, if I do this, it works. If I do this, it fails. Now that's a clue as to where the root cause is. Yet you still need to be able to explain it to your physics professor, is my opinion. Now we have all kinds of tools. We could do a whole podcast or webinar or a whole website just on root cause analysis tools and techniques. And the idea is that getting the circuit board and going, oh, well, that op amp failed and you replace it, now it's working. Yeah, it's turning on and off, but why did that op amp fail? Was it too many cycles? Was it too high of power being put across it? Was it fractured in manufacturing? And now you can see where this brainstorming with 3, 4 people going at it can really make it a much more fruitful to get to the underlying, well, why did that op amp fail? Now, a client of mine years ago had this a way of looking at a component failure of any kind of system. Was that component a victim? Maybe the power supply was putting out spikes of voltage, or maybe some other component was adding a load that wasn't designed to be loaded at that point. Was it just a victim that it just got beat up? It was the weakest link in the chain of wherever the stress was, and it failed. So replacing it doesn't solve the problem, because it's going to get beat up again by whatever was causing that problem. Or was it the hero, like a fuse in a system? The fuse fails usually because there's been overstress. That's what it's supposed to do. So it's not really a failure. Yet, if you just replace the fuse and say, oh, we're good, you're obviously not getting to the root cause as to what was causing the fuse to fail. And it's that kind of idea. So if you isolate and say, oh, this component failed, and you replace it, you're probably missing the whole story. And so the root cause analysis is that, why did it fail? How much force? Where did that force come from? How did that stress appear? And what does it take to replicate that problem? And that's what we mean by turn it on and off. Can we fully understand and replicate it at will? And start with the observations that you can make without touching anything. Then go to non-destructive, like probes looking for voltages and visual observation, and X-ray and CSAM and a handful of others that are non-destructive, and then do the cross-sectioning and taking components off and so on. In electronics in particular, if you remove a component, you pretty much destroy the evidence that could be your problem, the solder joint. So if you remove the solder, and that's where the crack is, and that's where the problem was, now you've just destroyed that evidence. So do the non-destructive first, then do destructive. And I'll probably say this way too many times in this presentation, don't isolate it to a vendor's product and send it to them. It is 9 times out of 10 pointless. Now, there are good suppliers and vendors that we work with that have really excellent failure analysis capability. Most do not. We have, for decades, have pushed the cost down of everything that we buy into our products, into our systems, such that they don't have the money or bandwidth to do decent failure analysis. Of course, there are exceptions, and that's, in my experience for the last 30 years, pretty rare. So do not send the isolated victim, maybe, to a vendor and they'll say, yeah, it failed. It had too much voltage. You need to understand that, and you can do it faster and quicker and more accurately either with your own internal failure analysis labs. If you're a big enough organization, you should really have world-class labs and all of the assets to do the destructive and non-destructive type testing and evaluations. And it has way more benefits than just doing failure analysis. Or hook up and get an agreement in place that can be used on demand with a world-class failure analysis laboratory. Get the teams and the technicians that have the experience working with lots of the types of technologies that you work with and engage with them so that you can take them the whole product or the whole board or the whole issue and say, hey, we need to understand why this failed. It's not just what failed, but why did it fail? You need labs and technicians and engineers that can answer those questions. And 9 times out of 10, in my experience, the vendors don't have that ability, nor do they have the incentive to say, oh, yeah, we screwed up. Plus, it may not be their fault. Remember, that component or that element of your system may just be a victim. So I could do a whole rant on sending to vendors. So what's your take on sending stuff to vendors? Or do you not do that? Hopefully. But what's your take on it? Maybe there's a couple of vendors out there that actually do a good job and others could learn from that. Repair and replace. Yeah. I've seen it where they say, all right, well, years and years ago, Dick Moss told me about, he says, vendors often have one of five standard answers. And he only answered four of them. He says, well, the fifth one is whatever they want to say that's not their fault. But, oh, you overstressed it. Or, oh, it's ESD. You haven't even seen the product yet. Well, it's always ESD, and so on and so on. Two or three good vendors that did design changes based on our findings. That's cool. Yeah. And as two or three, Dan, and I know that you have some experience, so it's probably out of hundreds and hundreds. Material issues. If some organizations really dive in and want to understand it, and I tend to want to work with those vendors because they're working on that continuous improvement idea. Yeah. And also, and Christopher's talking about it can take a long time to get the answers back. You need a solution sooner than later. So if you're paying for the failure analysis lab and you can get results in a couple of days or a week, that may save you 3, 4 weeks or longer to get similar information back from a vendor if they even provide it. And oftentimes I go back to is that failed component really might not be the reason that it failed. And we need to have, if we send the whole system back to the vendor for their one, say, op amp in it, they don't have the experience or expertise about the circuitry and about our system and where that all worked. So let's work with somebody that knows our products that we can work with to get to that kind of information. So, yeah, lots of things wrong with sending it to vendors. I hope that's not a default. And if you find good ones, really work closely with them and keep that going. All right, now we get to notice this is step 5 in this 8-step process. The true corrective action. All right. It's not oh, I know the problem. I know the solution and I'm going to go do it. And others are, well, if we just mask that alarm, then nobody will know it's failed. Those aren't real problems to the root cause of the problem. Yet the problem is that it's always a trade-off. It's going to cost money to make changes. And how much scrap are we going to involve? How likely is this failure to occur? Um, can we afford to not ship until we get the problem solved, but still understand that we're going to have 5% field failures, higher than expected, and so on. There's always a business element to how we actually implement a change. and how we roll it into a program. So it often takes, we really need to understand the root cause, but then we also need to figure out how do we actually implement that change. Now, this may take many rounds of like, well, I'm thinking of a fishbone diagram. You might have 150 different possible reasons or influences on this problem. Once you get to a true root cause, there may be multiple ways to solve that problem. It may be a process change, it may be a design change, it may be a vendor change, and so on and so on. Which one's right? And so that may iterate with doing the verifications. Let's do the experiments. Let's do the characterizations of which solution fits with our circumstance at the moment. Yet all of them have to solve the root cause, the underlying problem that's occurring. But it's not just physics and chemistry, it's also part of our process. Where did we make the wrong decision? Where did this process get out of control? Where did this vendor's monitoring of their process get out of control or cause issues? You know, I don't know how many times I've worked with vendors and I do the failure analysis and I show them the type of issue or the chemistry that we're dealing with has changed and they go, "Oh, we didn't think you'd notice." Well, it just caused us to have 50% failures. We did notice that. And it may seem like a benign change for somewhere in your supply chain, yet it can have devastating consequences later on. So we call that the escape point. What part of our overall process and includes decision making that went awry? How do we identify what went wrong where such that this issue, this problem, this underlying cause got through? And can we implement a change to the root cause and then monitor it at the escape point so that we can tell if it really got solved or not? And also, if you're only doing end-of-line type testing on your products, as you know, in continuous improvement, is you want to move that upstream as much as you can. And you want to move your monitoring and your uh, process control type activities to what's called an escape point in many cases. And it can happen. So part of this is where we work on and identify what's the right business and technical solution to this problem. And then it's implementing it, right? We got to go figure out how are we going to do this? Are we going to roll it in? Are we going to stop everything and retool everything? Are we going to change the design and then verify it? Or what's the plan? How do we do this? And that might take a different member of the team. It may take somebody that has more project management or more in the manufacturing operations type realm to fully under in customer support teams. So you may expand the team slightly to figure out, well, how do we implement this? Now, one part that I've often seen is that in the last step and this step is what else could this do? We need to step back and say, if we make this change to the process, and it's going to take us 13 seconds longer to create this step in the process, okay, that might actually solve the problem. What's the unintended consequence? Can we make our commitments for shipping? Do we have enough space to handle that that delay in the production line at that point? Do we have buffers and so on? What are the unintended consequences? And stepping back and brainstorming that is often really hard to do because you're so focused on solving this particular problem. Yet it's a part of the Henry Petroski's book on design paradigms. It's where we solve one problem, but we cause two more. Part of failure analysis is understanding, does the solution cause other problems or inconveniences or trouble? And I highly recommend that gets built into your system is what else does this solution cause to happen? Are we going to have to retool because now the component's a different size? If the solution is great, but it costs you $10 million and you're down for 6 months, is it the right solution? So part of those trade-offs comes into what else happens. Now, all too many people at this point just stop. We solved it. It works. We can get back to our day job. Right? That's unfortunate. The biggest part of the value of a failure analysis, especially when it's a team-driven one and it's deemed that, yeah, we need to solve this problem in a systemic way, is that we stop before we make it systemic. If we only change one design and that's it, yet we use capacitors or op amps or power supplies in many of our products. If we don't look at those other products and processes and say, how could this failure occur over here? Or maybe it already is and we just haven't seen it. But that takes time, it takes energy, it takes curiosity and some more brainstorming to figure out, well, what else could go wrong with this? My favorite example for this is ceramic capacitors. They're multi-layer ceramic capacitors are ubiquitous. It was my word of the day, by the way. And they're on all kinds of electronics, small and big pieces, and they're getting smaller and smaller all the time. But you have to remember, and your design team and production teams need to remember that that piece of ceramic is like a little piece of glass. If you push in the center of it too hard, it will break. If you hit one end of it with a very hot soldering iron, it will break. If you bend the circuit board, it will break. It's a fragile, small piece of glass, is the one way to think of it. Now, the problem is, which is why breaking a capacitor happens so often, is that in most of the electronics end-of-line testing we do, it's just really to check, is there a capacitor there? And capacitors generally look like an open circuit. It's once you put power on it and you can see the charge getting built up and so on, that it actually holds some capacitance, which is very difficult to measure quickly on a end-of-line test. Then it's really hard to tell if that capacitor is actually there or not. And even more so when it's just cracked. So it might have a slightly different capacitance value at this point. And it may be within the circuit's requirements. It may work. The issue is once a crack starts, it propagates. Thermal cycling will cause that crack to move, and eventually, more often than not, the capacitor will just simply fail to function as a capacitor anymore. It'll truly become an open circuit. Now, in some cases, that doesn't matter. It depends on where this is in the circuitry. And other times, it's crucial. And the root cause could be a blunt force or a high temperature or a bend or something else that causes capacitor break. But keep in mind, we use capacitors everywhere. And so when I was at Hewlett Packard, we ran into a problem that there was a crack in a capacitor and it failed in a very bad way. And I was asked to go figure out how often would this occur. Talk about a reliability challenge. And I did some material science folks got involved. I talked to the senior engineers at the vendors and got some more details about why this crack propagated into this kind of a failure and so on, and got a really good understanding of the problem. And we solved the problem for that one product line, helped them understand it so they could implement a change. Yet what we did is we did a webinar really quick across the entire corporation that said, hey, ceramic capacitors crack and they can do this or this or this, and you don't want the last one. And the other ones aren't good either, but here's where the possible sources are and here's why it occurs. And so we did some education, and I very quickly got phone calls from a dozen different divisions asking about more details and help my assistance in helping them solve their particular problem. And all it took was sharing what we knew about that failure analysis and what we'd learned over the last couple of weeks to help our peers in our organization and our peers across the industry understand that problem and avoid it or get to a solution much faster. And the last part is one that almost nobody ever does is, do you have design guidelines? Do you have operating procedures or design review checklists or whatever it is that you use to capture lessons learned? Did you update it? Is it changed? So if you change the process in a manufacturing line and you don't tell anybody, is it really changed? So there's some issues there. The final part, and I didn't put it in its own slide, is you need to formally close the project. Now, some teams, and I ran into this in a couple of organizations, is that they'll have a program manager and 30 or 40 people working on a problem, and they have their own budget lines and everything else, and they formally close the project and close out the books and reassign everybody. Others are much more common that it's informal. The four of us are going to get together as much time as we can to move this thing forward and get to a problem, get it done. Yet it's worth, and it's good project management to say, all right, we need to wrap this up, document what we have, get it in a place where people can find it in the future. Um, I'm looking at closure there, and I'm not sure I spelled that right. Sorry about that. But the idea is that you need to wrap it up. Say, all right, we're done with this, and we're moving on, and we can reassign that time somewhere else. And I've heard one organization was doing a D7 process, and they said, we don't do no pizzas for engineers. And it says, well, that's unfortunate because being successful at solving a problem and reducing your field failure rates or improving customer satisfaction and so on has a tremendous benefit to your organization. You can afford some pizzas or at least some recognition. But the idea is to celebrate failures. And even better when you have actually solved it and gone through the effort to truly solve the problem. And this is after you verified the issues, you know that the work is done, you've got it documented and detailed, you've got all your documentation updated, you've alerted other similar products and product lines and systems of this potential issue. Now let's close it up. And the recognition reinforces that you want to be on one of these teams. And it gives you a sense of completion, of success. And avoiding it, it just means it's not really appreciated from an engineering or management point of view. And yeah, they just saved you $20 million, but you can't afford a handshake and a recognition. Come on, do it. All right. Last few minutes of this, I'm going to go over some of the issues I see with any failure analysis, whether or not you use 8D or not. Let's see. There's I have never seen an issue identified and then alert a handful of other people, and there's usually somebody that says, "Oh, I can solve that," and they walk away and think they're in charge now and they have to go solve it. Sometimes it works. Some people say, yeah, I really already understand that problem, and they are the right person to go solve it. Yet I've seen it where it's a whack-a-mole. They think they got it, they fix one symptom, but not the real underlying problem, and then it still shows up, but in a different way. And then somebody else says, oh, I know what that is. And they go fix that symptom and so on. And it's just a whack-a-mole until you get to the root cause. And implementing a solution without really knowing if it's the right solution. I mean, really knowing it being you can describe it in detail, turn it on or off. You have true root cause understanding of why this issue occurs. There isn't really a practical way to justify a solution at that point. Now, if the person says, I know the solution, it's right here in the code and it does this to this component. And if we have this resistor here, it'll cause this voltage, blah, 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 blah. And it makes sense, passes the gut test, then say, all right, yeah, let's go for it. I find that without that deeper understanding and the ability to describe it, it's generally a waste of time. If you can't describe the root cause in detail to your peers, you probably really don't understand the problem yourself. Yet organizations value time as much as anything. If we have a problem that shut our line down, what are we going to do in the next 10 minutes to get it up and running again? And that leads to this jump to solution type thing, because then you could be the hero. If you're not, well, they trusted you when they shouldn't have, kind of thing. The other issue I get is that it's an all hands on deck. Now, if you're shutting down a line and it's a safety issue, that may be the appropriate thing to do. All right. And yet, not every issue is all hands on deck. And by that, I mean everybody in the organization, stop what you're doing. We're going to solve this problem. Now, that's a logistical and management nightmare, is to change directions very quickly, especially if you have a large group. Now, having said that, sometimes it is useful, but it's, like I said, it's not every issue. So having that good triage ability that can get the right people together at the right time to say, yep, this is, here's the path, here's what we should do, here's what the team should do, here's what the rest of the organization should do. All right. I was in a factory and it was in Houston and it was making some electronic system, and an operator on the floor hit the, not the emergency stop, but it was an emergency stop, and it was a call to address an issue, a problem. And the person that hits the button then goes straight to this conference room, or war room, they called it, and a handful of other people stop whatever they're doing, including some pretty senior managers, come down and they listen to what the problem is and they make a set of decisions. They do triage within seconds of the issue being detected. And the one I observed is the per person on this manufacturing line who was making circuit boards noticed that it had the wrong value of component. The wrong component was being installed on these products, and stopped the line, which is actually a pretty smart thing to do. Went and explained it, and they immediately got a hold of a couple of manufacturing engineers that said, "Oh, this has been on the last, 35 pieces, and it's still on the machine. So we have a total of 50 units that are involved." And they said, isolate those 50 units, put in the right component. And do we have the right component? Put that in place. Check what we have that hasn't been boxed yet. Make sure it hasn't been ongoing for a little longer than we expected. And then restart the line. Total time was less than an hour. And it reinforced for that person, that engineer or technician on the line, that it's okay to stop the line. This was a valid reason to do it. And they didn't get chewed out. They didn't get, docked for shutting the line down or anything else. And sometimes there's false calls. But if you have a real issue, and you don't want your team just to look the other way, because there's not a viable way to actually immediately take care of it. And so sometimes that meeting, they told me, then is the line's down. And now we got to get engineering teams and all kinds of other people involved and bring in some experts, and it might take us a week to solve the problem. Yet it was okay for anyone, if they notice a problem, to stop the line. And it worked. It made more ownership on the production line. It really reduced their field failure rates and their scrap rates. It made a big difference. On the opposite side is you all know these operations managers that, what's it take to get it running immediately? Independent of what the nature of the problem was and how much damage was done and on and on and on. It's get it running. There's a lot of pressure to keep production going. There's a lot of pressure to meet your deadlines. The trade-off is, if you continue to make poor or bad products, your entire staff will be okay making poor and bad products. And at the end of the day, it's your customers are going to judge this. Your stockholders, your shareholders, or key stakeholders are going to care about this. And yeah, making your numbers for end of quarter is one thing. Continuing in business is another thing. So I looked at some really good ways to do this to balance the urgency of getting back up and running with the urgency of really understanding the failure mechanisms and solving the right problem. It's always a delicate balance. It really depends on the culture of your organization and what they actively do to reinforce the behaviors that they want in the organization. So if it just start to never stop the line, yeah, it's really hard to say I'm going to make any improvements because management really doesn't care that we just ship bad products or the yield is up. So it's up to us to help set some of those things. And some of us have a position where we can make those changes, but these are real problems that we all face when it comes to identifying a problem and trying to find a solution. I mentioned it early on. When you first identify something has failed, and we talked about it briefly and a lot of input on it, what we mean by that. It really is, I think, a good way to think of it is that, TV crime scene drama type stuff where there's yellow tape around it and cameras and taking plaster prints of tire tracks and stuff like that. Just gather the information you can without destroying any of that information. And if that means don't touch it, it means don't touch it. If you pick up a product and you put your thumb on it and you have a bunch of ions, chlorines, and bromines and stuff like that on it, that may taint the investigation of what caused the corrosion that actually caused the failure. Now we're muddying it up by putting a bunch of extra stuff there that may or may not have been there to start with. Don't take a component off the circuit board until you've confirmed the solder joints are sound. Duh. Come on. And please don't send it to a vendor. All right, enough said on that. The full benefit of a failure is that it helps you understand and solve an immediate problem, the one you just recognized. Yet the solution can go back to design criteria for lessons learned for how we do things here, to how do we manage and control vendors so that we get the quality of products we want. It can go into decision making during design reviews or even design of engineering of the product design or the manufacturing process design. The benefits that come out of identifying and fully understanding a failure doesn't just solve one problem, it helps us to avoid a whole class of problems going forward if we do this last step. And way too many organizations fix the problem and move on. And they really don't use a good way to do lessons learned. And I did one, I think it was called Golden Nuggets or Lessons Learned Golden Nuggets, something like that, webinar a couple of years ago, which is by and far the best system I've ever run across for lessons learned. And it's a great thing to have at the end of a failure analysis process is, does this qualify to be part of our ongoing lessons learned system? And you can have all the details somewhere else, but you need a way to say something like ceramic capacitors break, or some other, usually get somebody in marketing to come up with good ways to describe problems. But it's not just this capacitor from this vendor, it's in general. These components are fragile, or whatever that particular problem was, is that, yeah, if you put 1,000 volts across a capacitor that only can take 5 volts, of course it's going to fail. Where in the world did that 1,000 volts come from? Let's understand the circuitry such that now it doesn't occur across our low voltage components. And things like that can show up that allow design teams to keep conscious the underlying causes, the decisions that cause problems to come back into our systems. So the lessons learned is the ultimate benefit, I think, if it's used uh, to our failure analysis activities. All right, I'll leave you with this question, and actually finished a couple of minutes early. I probably talked too much. But the idea is that we can really learn a lot from failure analysis. Are you? Oh, Shahid's question is don't send it to the vendor. So let's say you're working on a product and you buy power supplies and the power supply fails, right? It has some smoke coming from it or doing whatever it's doing. It's not working. You plug it in and you get no power. Now you can box it back up and send it back to your vendor that you're buying the power supplies from and say, hey, this failed. You need to do the failure analysis and fix it. Now, my experience with failure with power supply vendors is that, excuse me, my experience with power supply vendors is they'll probably take 2 or 3 months and probably blame you for whatever reason they can come up with that you caused the failure, which isn't helpful for them or you. But the issue is that, yeah, they know a lot about their product. They know about making their product. Yet, as I mentioned earlier, is that we often have not paid our vendors collectively across industries enough that they have a world-class failure analysis outfit. They don't have x-rays and cross-sectioning and as, scanning electron microscopes and so on, which may really be necessary to fully understand a problem. And that includes material analyst capabilities and chemical capabilities and so on. If you really want to understand the problem and you want to do it in a timely way, send it to a truly neutral or internal failure analysis lab to get a true understanding of what failed. Now, if you can identify that the problem is really part of the vendor's process, and I've done that multiple times where the initial thing is, hey, did you change anything? We're seeing this problem. Oh, no, no, no. All right, I go to the lab, excuse me, and I find that they changed the chemical composition of the dielectric solution that's used in electrolytic capacitor. And I send them the chemical analysis. And they say, how do you know that? I says, well, I took it to a chemical lab and analyzed it. Well, yeah, we changed that, but you shouldn't notice that. I said, we do. Is this really the problem? What are you going to do about it? More times than not, if you take the evidence to the vendor that it really is their problem, you can get to a solution with the vendor much, much faster. If you just take the problem to the vendor, 9 times out of 10, it's not our problem. Something else in your system caused this. And that may actually be a true statement. Or it's not our fault, man. It's somebody else did this. Or we knew about that and it got solved and don't worry about it. And so on and so on. It's really not helpful vast majority of times of sending the isolated component that you believe is the cause of the problem back to the vendor. It's spend the time to do that analysis yourself and then go to the vendor if that's where you need to implement a solution. It saves you a whole lot of time. It brings the vendor needed information so they can understand the problem and make changes. It just saves everybody a whole bunch of time. So if you isolate a power supply saying, oh, it didn't work, and send it back to the vendor hoping that that will solve all of the problems, yeah, dream on. That rarely happens. Now, of course, there are exceptions. I know that, but most of the time it doesn't happen. So hopefully that answers your question a little bit. Yeah, they throw it back to you, but sometimes they don't have an option. It's yes, this failed because you plugged it into the wrong outlet and it got overpowered. It's not their fault. And sometimes they don't have the ability to actually tell what happened. And it's part of the consequence, unintended consequence, in my opinion, of driving our supply chains to the minimum cost in so many industries. So Yes, please, if you take nothing else away from this discussion and diatribe, is don't send failed stuff back to vendors unless you really understand the root cause and can share that with them so that they can make a change to your benefit and to their benefit. Otherwise, most of the time it's wasting time. All right, good. Got a handful of questions. Let me take a look at anything else. A couple of links in there, a couple of good stuff in there. Thanks all for participating, all the comments. If you're listening to this on a podcast or on the recordings, there's usually a way for you to get in touch with us online or on a podcast. It's at accendoreliability.com/go/SOR, which is a different podcast, but you can use that to get in touch with us. It's easy to remember. Or get back to us on the site or directly to us. There's plenty of ways for you to get in touch. So looking forward to one more episode or one more event this year, early in December. I think Chris is coming back the fourth Tuesday of November. And then we're starting to sit down and figure out what we want to do next year. So look forward to ongoing discussions and appreciate all your attendance. Have a great rest of your day.